Virus. In this exercise, we'll study the dynamics of a virus among a population of n individuals. For this, we'll define different state variables. So I will explain just now what it means. So we'll classify the population into those who have not yet been infected, those that are infected and they are capable to spread the virus, and those that have been cured. And what we want to solve is to find the state equation of this system of the propagation, taking into account some assumptions that I will now explain. So I consider here the world with a population in blue, so I will call it x1. This population, the population of individuals that have not yet been infected. So I represent this population like this, and among this population, you will have in this world some other in red that have been infected. This one, this one, this one, and this one. We have also another population. So this one was correspond to x2, infected. In blue, not yet infected. And in green, x3, cured. So they have been infected before, but now they cannot be affected again, and they cannot transmit the virus to others. Okay. The population is n, the total population, is the sum of x1 plus x2 plus x3, so this number should be huge. And let's say, for instance, 100 million, for instance. Okay. So we can see this word as follows. We have, it is a compartmental model, where here it is a population, so x1 is a number, x2 is also a number, x3 is a number of population that have been cured. Here I have the people that have not yet been infected. Here those that are infected, and in green here they have been cured. And we can understand that we have this situation where some people that have not yet been infected can move to this state, and those here later they will be able to move here. So it is what we call this kind of system that satisfies this. It is a compartmental model. Okay. So the assumption one we take is, and we can understand this, is an individual in the population which has not yet been infected, so the blue, has a probability to become infected at each unit of time, which is proportional to the density of infected individual. So what that means? It means that a blue individual here, not yet infected, which move around, will meet some other people in the population, will meet green, and will meet red, and so on. If I take this number of red, if I multiply by 2, so here I have 4 which has been infected, and multiply by 2, so I put 4 other like this. Then the probability for a blue to become red is multiplied by 2 also. So it is the assumption 1. The assumption 2 now, what I consider, is an individual which is infected at time t has a constant probability to become cured uh, at each step of time. So it means that this one, which has been infected, can become green, like this. Okay, and this probability does not depend on time. It is an assumption that which is not always true, but we will assume this here in this model. So the first question that is asked is to find the state equation of this system. For this, due to assumption 1. Assumption 1 tells me that the evolution of the blue is proportional to proportional to the population itself, of course. But since the probability to be infected is proportional to the number of infected individuals, it means that I will have something like this. So this is the quantity or the probability to have in a neighborhood someone which is infected. And since it is proportional, I put here P2 and a minus. And the minus means that the number of not yet infected people can only decrease. And the rate of decreasing is this, is proportional to the number of infected individuals. Now about the assumption 2. The assumption 2 tells me that the number x3 of cured people will increase, of course, and it will increase proportionally to the number of infected people. So number of infected people is x2, and I have a coefficient p2. So I have these two parameters. Now to find the state equation, I also need to take into account that x1 plus x2 plus x3 equal n, and the total population. As a consequence, x dot 1 plus x dot 2, the derivative with respect to time, is equal to 0. So equivalently, it means that x dot 2 equal minus x dot 1 minus x dot 3. Or equivalently, x dot 2 equal excuse me, here I have p1 and p2. There are different coefficients. So I will have x dot 2 equal to p1 x1 x2 due to this. x1 x2 divided by n minus x3 dot. x3 dot is here, so minus p2 x2. So as a consequence, the state equation that I need to find are x dot 1 equal minus p1 x1 x2 divided by n, and x dot 2 is equal to p1 x1 x2 divided by n minus p2 x2. So note that x3 is not inside the state variable, because if I know x1 x2, then I can guess from the total population the value of x3. Recall that indeed the state variable should be independent. Moreover, it is state equation, because if I put x equal x1 x2, then I have here an equation of the form x dot equal f of x, where f of x corresponds to this. Question number 2. I have to identify the parameters p1 and p2 of our state space model. And for this, we will assume that, assumption number 3, that a not yet infected individual which lives among a population totally infected, then the probability to be infected 1 day later is 0.3. So it means that if I have a huge population of 100 million people, if in this population I have 100 which have not yet been infected, whereas all of the others are infected, then the day after, 30 of them, so 30 among the 100, will be infected. So it is the assumption we take. And this can, for instance, be estimated by statistic in this population at the beginning of the apparition of the virus, for instance. Now, the other assumption is the following. If one individual is infected at time t, so it is totally separated from others, if you want, then it has a probability of 0.1 to be cured 1 day later. So it means that if I have 10 people that are infected, the day after, 9 of them will still be affected and 1 will be cured. From this information, I have to identify the parameters P1 and P2. So from the assumption, question number 2, from the assumption A3, I consider that since everybody is infected and the population is huge, I can consider that x2 corresponds to n. It's approximately equal to n because everybody is infected. It means that x2 divided by n is equal to 1, approximately. So this term is approximately equal to 1. As a consequence, x dot 1 equal minus p1 x1. Now, due to the fact that the assumption tells me that if a not yet individual lives among a population where everybody is infected, has a probability of 0.3 to be infected, I have this term which corresponds to the evolution rate, which is equal to 0.3. Now, I will take the assumption 4, and from the assumption number 4, which I recall now, the assumption if one individual is infected at time t, then it has a probability of 0.1 to be cured. So it means that since x3, so I add this relation here, I take this relation here. X dot 3 equal p2 x2. From this assumption, I deduce that p2 is equal to 0.1. Question number 3. When t tends to infinity, we would like to study the percentage of population that will never be infected. For this, we need to study the equilibrium points of our dynamical system. Question number 3. My system is described by x dot equal f of x. I have no more evolution where x dot equal to 0, which means that f of x equal to 0. So this happens when from this it is equivalent to say that this quantity is equal to 0. So we see quite easily that since x2 is in factor to all of them, which it is equivalent to say that x2 is equal to 0. As a consequence, I may x1 and x3 can have any value. So we cannot say anything about x2, x1 and x3. It depends on the initial condition. So we cannot answer the question. We cannot know from the dynamic of the system what is the percentage of the population that will never be infected. Question number 4. We assume that at time t equals 0, we have only one infected individual for a population of 100 million. And we'll be able to predict from this initial population what we wanted to know at the previous question. We'll be able to know what is the percentage that will never be infected, but more than this, we'll be able to predict at which time the peak, I mean the maximum number of infected people will occur. For the simulation, I propose the following Python program. So first, I have to program the evolution function f of x of my system, which is given here. And then the initial state is I have the total population, which is 100 million. So everything is in million concerning the population. So 100 million. My coefficient parameters that has been identified to 0.3 and 0.1. I will simulate for 200 days. So here it's days. And the sampling time for the simulation is 0.1. So I needed for the Euler formula to integrate this equation. Recall indeed that if I have a state equation of the form x dot equal f of x, then the Euler method tells me that x at time t plus dt, where t is small, so here small means 1 day divided by 10, so it corresponds to something like 2 hours, 2.4 hours, which is small compared to the time constant of this system. It is equal to x of t plus x dot of t multiplied by dt. So it is the Euler formula where this one is equal to f of x due to this. And this is what is used in the program to simulate the evolution of a differential equation, such as it is the case here. The Euler formula is here, where x1, x2 is a state. At the initialization, I have here 1 divided by m1 million, which say that I have only one individual which is infected. So x2 is the infected people. x1 is not yet infected. I will perform my simulation. I will write time t, x1, x2, and x3, taking into account that the fact that x1 plus x2 plus x3 equal to the total population of 100 million. And here I will draw the corresponding graphic with respect to time of each of the state variables. The Python program, I run it. I see all numbers as since I print it here, and I can see the evolution of x1, x2, x3, and when t, this is my graphic. So I will try to interpret this graphic, which is given here. So x1, x blue. So it means at the beginning, everybody is not yet infected except one. One among 1 million. The one is infected is in red. So here one is infected. We cannot see it due to the scales. Now it takes time, but after a while, so here it corresponds to, let's say, 80 days, then we can see that the number of infected people start to be significant. And from the simulation, I can see here that I have a peak here. And in green, it corresponds to x3, the number of cured people. What we can see on this picture is that with some initial condition, then at the end, I will converge to a limit, and some people will still remain not yet infected. Okay, there is not enough people to infect them. And here, in a similar way, we can see that not all the population has been cured, which is consistent with this. But what is sure is that the number of infected people, so x2, at the end, I have no more infected people, which is quite consistent with the intuition we have on the evolution of the system. From all these numbers given here, I can see that the peak x2 correspond in my situation 30 million here, 30 million, and the corresponding time is 103 days. For the last question, we have to draw the trajectory in the state space and also the corresponding vector field. So recall that previously we had shown with respect to time t, we have seen x1 of t, x2 of t, and x3 of t. It was an interpretation with a population with respect to the time t. Now what we want to do is to have another representation in the x1, x2 space, which is called the state space because my differential equation has the form x dot equal f of x. So it makes me possible to draw the dynamic of the system if I am able to draw f of x. So how can I draw f of x? I take many points like this, and I compute for each of these points f of x, and it gives me a vector which corresponds to x dot, the evolution. And the evolution gives me a vector field like this. If I interpret the vector field, then I am able to understand the evolution of the system. So for this, we'll use the function draw field, which has as a parameter the function f given here, and it will draw this field in Python. I will also simulate via Euler method, the Euler method, to draw the trajectory, and the trajectory follows the field. It means that they are always in the direction of the rows. This is my Python program, and I will run it here. And it is given here and the vector field has been normalized. I mean, all the vector has the same length. So it gives me the direction of the evolution. But if I want the real one to have a better interpretation, then I will put here in the vector field false. So means non-normalized. Then I obtain this. So I can see that the evolution is quicker when the rows are longer. So this is my two vector field. And the trajectory is painted red. So at the beginning, I am here because everybody except one, are not yet infected. So this is why x2 is equal to 0, or x equal to 1 because 1 is infected, and x1 is equal to 100 million people. And this is the evolution, and this is the maximum for x2. It corresponds to the peak. We can understand that the evolution, I go slowly at the beginning, but I cannot see the time, so I will present like this to say that I go slowly. So it corresponds to the day here, and the day become larger when the arrows are long, and after it becomes slow like this, and after very slow. So it is important to have this vision with respect to the time if we have to take some decision, because if, for instance, we ask a different policy about how people should behave, then I can change the orientation a little of the row by decreasing the evolution of the infected people. So if I start from here with a different policy, it will change the orientation and obtain another trajectory. But it has a cost. So it is better to focus on some period where the evolution is fast, because the impact for a given cost will be stronger. So for instance, if I want here where the rows are big, here I ask people to stay home, then I will have at the beginning, since I do not change my policy, something like this. Here I will change the orientation of the row. I will go here, for instance. So no more infected people, and after I will converge to another point. So the peak will be lower, and if I ask for the same policy here or here, the impact will not be as big because the evolution is less faster than here.